Have you ever stared at a weather app and wondered, how many days till it gets warmer? Daily Temperatures is a Pattern Mastery 100 favorite that silently checks your mastery of the monotonic stack, a pattern that powers dozens of array problems at Phong. We'll turn scattered temps into instant answers with a clean ON sweep using the basic framework. Let's go. We have an integer array temperatures. For each day I, we must return how many days you'd wait until a warmer temperature. If none exists, return 0 for that day. Output is an array the same length as input. Brute force is ON squared, checking forward from each day. Instead, use a monotonic decreasing stack of indices. As we scan from left to right, we'll pop cooler days when today is warmer and compute their wait lengths in O1 each. Total runtime ON, extra space ON for the stack and results. Plan. Create ends filled with zeros and an empty stack ST for indices. Iterate days I from 0, N1, while stack not empty and temperatures I, greater than temperatures ST-1, pop J equals ST.pop and settings J, equals I, J. Push I onto the stack. Leftover indices have no warmer day remain 0. Let's try to implement it using solution 1. We begin by defining a solution class. This is the usual container so platforms like LeetCode know where our method exists. This is our main function. It takes in temperatures, a list of daily temperatures, and our job is to figure out how many days you have to wait until a warmer temperature appears for each day. We store the length of the list in n. This helps us build our answer list and loop through the temperatures. It is super simple and constant time. We create a result list filled with zeros. Each position starts at 0, which means no warmer day has been found yet. We will update these values as we discover warmer days. Next, we create an empty stack. This will store indices of days whose warmer future temperature we have not found yet. We will use a monotonic decreasing stack, which means the temperatures at the indices inside the stack will always be in decreasing order as we go inward. Now we loop through each temperature using enumerate, so I is the current day index, and T is the temperature on that day. We will check whether today's temperature is warmer than previous days we are tracking. This is the core logic. While there are days in the stack, and today's temperature T is warmer than the temperature at the top of the stack, it means we have finally found a warmer day for the day stored at stack of index -1. We pop that index J from the stack, which means we found a warmer temperature for day J. That day is now resolved. We record how many days it took to reach a warmer temperature. That is today's day index minus the previous day index. For example, if day 2 gets popped while we are on day 5, then res at index 2 becomes 5 minus 2, which equals 3 days of waiting. After checking for matches, we push the current day I onto the stack. We have not yet found a warmer day for today, so it stays on the stack until a future temperature beats it. In the end, the res list contains the number of days each temperature needs to wait until a warmer one appears. If no warmer day exists, it stays as 0, which is exactly what we want. And that is how this algorithm works. It uses a monotonic stack to keep track of unresolved days, then updates them as soon as a warmer temperature appears. Efficient, simple, and elegant. Let us test our function using this input. These numbers represent the daily temperatures for 8 consecutive days, and our goal is to figure out how many days each temperature must wait until a warmer day arrives. What the input represents. Each number is the temperature of a day. For example, day 0 is 73. Day 1 is 74. Day 2 is 75. And so on. Some days will have a warmer day ahead, and some will not. That is exactly what the algorithm resolves using a monotonic stack. Here is why the solution works. Our stack-based algorithm walks through the temperatures and keeps track of days that have not yet found a warmer day. Let us look at a few key steps. On day 0, which is 73, no comparison yet, so the stack is 0. Day 1 is 74, which is warmer than day 0 at 73, so day 0 waited 1 day. Day 2 is 75, which is warmer than day 1 at 74, so day 1 waited 1 day. Day 3 is 71, which is cooler, so it stays in the stack. Day 4 is 69, and it also stays in the stack. Day 5 is 72, which is warmer than day 4 at 69, so day 4 waited 1 day. It is also warmer than day 3 at 71, so day 3 waited 2 days. Day 6 is 76, which is warmer than earlier days and resolves several positions in the stack. Day 7 is 73, which is not warmer than day 6 at 76, so the last 2 positions get a waiting time of 0. By the end, every index in the output array correctly represents the number of days until the next warmer temperature. And that is exactly what our program outputs. This matches the expected result perfectly. Our implementation is correct. The algorithm successfully computes the number of days until a warmer temperature using a monotonic stack. It is efficient, accurate, and reliable. Now let's try another implement approach using solution 2. We start by defining the solution class. This is just the standard wrapper so platforms like LeetCode know where to find our method. Here we define daily temperatures. It takes in temperatures, a list of daily temperatures, and we want to return, for each day, how many days to wait until a warmer temperature. If no warmer day exists, we leave it as 0. We store the length of the list in n. We will use this to loop from right to left and to check bounds. This is O of one time. We create a result array res filled with zeros. Res at index I will eventually hold the number of days you need to wait from day I to reach a warmer temperature. If it stays 0, that means there is no future warmer day for that index. Now we loop backwards from the second to last day, which is n-2, down to day 0. Why backwards? Because we use information we have already computed for days to the right to speed things up. This loop runs n-1 times, so it is O of n iterations. For each day I, we start by looking at the next day, I plus 1. We will try to find the next warmer day starting from there, potentially jumping ahead using the res array. This while loop says, as long as we are within the array, and the temperature at day j is not warmer than day I, meaning it is less than or equal, keep searching further ahead. So we stay in this loop while we have not found a warmer day yet for day I. Inside the loop, we first check whether res at index j equals 0. This means that from day j onward, there is no warmer day, because earlier we already computed that for j. So if j itself is not warmer than I, and res at j is 0, then there is no point going further. We already know it will not get warmer from there. In that situation, we set j equal to n. This is a neat trick. It forces the while loop condition j less than n to become false, which signals that no warmer day was found for day I via this path. We break out of the while loop early because we now know there is no warmer temperature in the future for day I through this route. If res at j is not 0, that means day j does know where its next warmer day is. It is exactly res at j days ahead. Instead of moving one day at a time, we jump forward by res at j days. This is the dynamic programming jumping idea. We reuse previously computed answers to skip over stretches of days that we already know are not warmer, which makes it faster than stepping one day at a time. After the while loop, if j is still within bounds, meaning j is less than n, it means we did find a warmer day for day I at index j. In that case, we set res at index I to the number of days between I and that warmer day j. So if I equals 2 and we found a warmer day at j equals 6, we store res at index 2 as 6 minus 2, which equals 4. Finally, we return the res array. Each entry tells us how many days to wait until a warmer temperature appears for that day, or 0 if no such day exists. And that is how this algorithm works. It walks backward to reuse already computed next warmer day distances, then uses those distances to jump ahead and quickly locate the next warmer temperature for each day. Efficient, simple, and elegant. Let us test our function using this input: 30, 40, 50, 60. These values represent the temperatures over 4 days. Since the temperatures rise every single day, each day except the last one has a warmer day immediately after it. What the input represents, each number is the temperature of that day. Because the pattern is strictly increasing, this is one of the simplest cases to analyze. Every day finds a warmer temperature the very next day, except the final day, which has no future days left. Here is why the solution works. Our algorithm moves from right to left, reusing results to quickly determine the wait time. Day 3 has temperature 60. There is no future day, so the result is 0. Day 2 has temperature 50. The next day, 60, is warmer, so the wait is 1 day. Day 1 has temperature 40. The next day, 50, is warmer, so the wait is 1 day. Day 0 has temperature 30. The next day, 40, is warmer, so the wait is 1 day. Because the temperatures rise consecutively, every day except the last one has a waiting time of exactly 1 day. And that is exactly what our program outputs. 1, 1, 0. The output matches the expected result perfectly. So our implementation is correct. The algorithm handles strictly increasing temperatures exactly as expected and returns the correct number of days to wait for each warmer day. Let's have a quick recap. Breakdown recap. The problem turns courses and prerequisites into a directed graph. Each rule take A after B becomes an edge. The real question, does the graph contain a cycle? If there is a cycle, you cannot finish the courses. If there is no cycle, all courses can be completed. Assess recap. 2 approaches solve it cleanly. DFS with state marking, or BFS using Kahn's algorithm with in-degree tracking. DFS is direct for cycle detection. Kahn's algorithm is equally effective for building a valid order. Important details include handling multiple valid orders, disconnected subgraphs, and trivial cases like having no prerequisites. Structure recap. The plan. Build an adjacency list. Track each node's state. Unvisited, visiting, or visited. Run DFS on each course. If DFS ever revisits a node that is still in the visiting state, a cycle exists. Mark nodes as visited after exploring all neighbors. If no cycle is detected, the schedule is feasible. Implement recap. We built the graph, initialized a state array, and ran DFS across all nodes. We stopped early whenever a cycle appeared. The implementation ran correctly on LeetCode. Check recap. We tested successful chains, failing cycles, and edge cases such as empty prerequisite lists and disconnected components. The solution behaved correctly across all scenarios. Key insight. Dependency problems reduced to cycle detection. If you can model the graph, track node states, and reason through recursive exploration, you can solve any ordering problem with confidence.